Well, we've developed how we use thermodynamics to accurately calculate the energy released from chemical reactions. Now we turn to this question of how heat and work are related, because it turns out that thermodynamics informs us of exactly how to do this, but also in the course of that it tells us what we face in the future and which pathways from now into the future are viable from a thermodynamic point of view. And this reminds us of a number of issues. The first one is, why is 65% of all primary energy generation wasted? We'll see that the answer to that lies in the analysis of how heat is converted to work in a heat engine. And a heat engine is common to all of us. It's the engine in our car. It's the way in which electricity is generated by burning natural gas. It's the way in which all fossil fuels that produce heat are used to produce work. The second aspect is, why is a gasoline automobile only 15% efficient in converting chemical energy to effective work? That is, if we add up the energy that we've just calculated from octane, which is gasoline, and we actually determine the work that can be done from the chemical energy determined by the delta H of that reaction, it turns out only 15% of this goes into the effective work done by the automobile. And we'll see why thermodynamics tells us this will never substantially change. The next thing thermodynamics tells us is how to heat and cool our homes far more efficiently than, for example, burning natural gas in the basement. And this involves the secret of the heat pump. The heat pump takes a small amount of work, adds to the temperature of the surrounding atmosphere, and puts that into our house. And it turns out that a tiny amount of electrical energy can produce much larger amounts of heating and cooling. Next thing is, why, when Elon Musk founded Tesla Motors, how did he know his business model was going to succeed? And he knew because, first of all, when you drive an electric car, you realize how superior they are to a gasoline car. But he also knew that electric motors are 95% efficient, whereas gasoline engines are 15% efficient. Also, an electric motor produces no carbon output, no CO2 output that contributes to the trapping of infrared radiation, as we saw in the first two chapters. Also, how does the first law of thermodynamics fundamentally change the debate regarding the risks associated with climate change? And we'll see the climate debate should not be about global warming, because temperature is not the variable of interest. The variable of interest is the flow of heat into subsystems of the climate that are irreversible. And the first law of thermodynamics tells us exactly why this is the case. Also, what will be the trajectory as we shift from current fossil fuel use to renewables? Fossil fuel extraction, distribution, and combustion is an $8 trillion a year enterprise globally. But we'll see that the economic factors that come directly out of thermodynamics tells us precisely how quickly we need to terminate the release of CO2 from fossil fuel combustion. And finally, where are the most important frontiers in research and technology developments in energy production? Thermodynamics tells us very clearly where those frontiers are.